So the next presentation, so it's done by Marc Boyer. He is currently a research scientist within the National Office for Aeronautical Studies and Research in Toulouse, ONERA. His research interests focus on embedded networks and AFDX, or TSN AFDX, and performance of those networks, mainly using the network calculus theory. He will present about designing a resilient, time-aware shaper configuration for TSN. So, stage is yours.
So, thank you very much. So, I'm going to present work that has been done in a joint project with people from Thales Research and Technology, especially Rafi Kenya from Thales Group, and he's not here today. I'm going to present it. And the name of the project was Resilient TSN. So what is the general context? So we consider that we have a TSN network. Okay, so you know what is it now, and because when I've done the slide, I was not aware that Jonas Farkas would be presented before. And so we assume that we have a set of real-time data flows that are called streams in TSN, and we have an initial static configuration. And the problem we want to address is that sometimes we may have faults. Okay, we may have some data links that are broken, perhaps one link, perhaps two links, perhaps three links. And the question is, could we do something? And that's the question on the starting point of the project. So we address permanent link fault, okay? And the challenge are, what are the challenges? So when you have some links that are down, okay, you need to find new routes. Okay, that's the easy part, having a new path. The problem is to allocate resources to get real-time performances with what is remaining. And that's a hard problem. Especially if you want to do this in short time. We have no formal definition of what is short, will depend on the use case. And if you want more details on the use case, you can find it because we have already presented at another conference, IEEE-SA, and so you can download all the use case, and there is a GitHub, you can find all the streams and so on. So that's the general challenge of the project. And today, I'm going to present just one subpart, which is the reconfiguration of the time-aware shaper. So I need first to present time-aware shaper, because perhaps not everybody knows all about this. So time-aware shaper is a time trigger shaper, meaning that we want each frame to have a dedicated time window, and each frame must be sent during this time window. So here is a small example. We have of a very small network. We have three streams, A, B, and C, and B, okay, going this way, C is going this way. And they all stream have the same period for this example, which is simple. And so we assume that, for example, we have an initial design, which is this one. We assume that the first frame that will be sent in this example is A1. So it has a reserved time slot on the link between end system 1 and switch 1. Okay. And once it is received in switch 1, it has another time slot, okay, on the next link, and there is a time slot here to get to destination. So C1 is exactly the same kind of behavior, but that is shifted, okay, and that's so both A1 and C1 has very short latency through the network, and B1 has a slightly different behavior. So A1 is emitted just after B1 is emitted just after A1, and we assume that B1 could have a deadline that is not so strong than the others. So it is delayed in switch 1, for example, to use this time to send lower priority data. Okay, of course, on this example, it is so short that no frame can be sent, but okay, on a real example, it can happen. It can make sense to delay frames because they have time. And then B1 reach its destination. And then we have another cycle with A2, B2, etc., etc. So we have 3 cycles. So TAS is a fragile mechanism, and for example, it's fragile to losses. Now assume that the task that was supposed to put A1 in the queue has not been executed or has not produced A1. So when the windows start, so I have to say how windows are implemented in TSN. In TSN, windows are just implementing by opening and closing gates. So when there is a gray box, it means that the gate is closed. So if A1 is lost, B1 is sent instead of B1 because it's the first in the queue, and the gate is open. So B1 is received in switch 1 at this time, and because the gate is still open, it can go on. So A1 is going to take place of A1, and B1 will arrive, not in the advance, because at the end it will take exactly the same window. Now have a look on what happened for C1. So C1 takes its own window, but when it tries when it's supposed to be sent in switch 1, in fact B1 is using the output link, and then C1 cannot be sent. So no problem, C1 will use the window dedicated to B1, but now when it enters the second switch, the gate is closed. So we have a problem in one period. Now what happened in the next period? So for A2, B2, everything is okay. The only difference is that when the gate open here for between switch 2 and system 4, we have still C1 in the queue. So C1 will use the time window of that was dedicated to C2. And in fact, with such mechanism, we will have a permanent delay. C stream will be one period late infinitely because of a single loss of another part, of another flow. So what is the contribution that I would like to present? It's reconfiguration of time shaper, and we would like this reconfiguration to be incremental. So incremental means that the windows of existing flows, flows that are not impacted by the fault, are not modified. We like it to be fast, I would already say. And we will do that without updating the gate control list. So so I'm not saying that, sorry. The gate control list, I should say that, is a configuration parameter that says when we open and close the doors. So we want to do reconfiguration without changing the time of opening and closing gates. Why? Because it increases the deployment, because we do not have to deploy the new configuration. And we also avoid the problem of coherency of the system, because when we are going to shift from one configuration and the other configuration, it's hard to synchronize all shifts. And this scheduling will be immune to the problem of losses. So why do we care about incremental update? So what is incremental update? First, a definition. So we do not want to change the time windows of flows that have not been impacted by the fault. Why does it matter? Because data that enter the network, they are produced by task. And in time trigger systems, in general, people are synchronizing task and network, meaning that if we have a blue task that is creating a blue frame, the task will be executed between its release date and its deadline. And in general, it's common sense to have a time window just after the deadline, or not too late after the deadline. Then, but if I compute a new network schedule that is independent of the first one, I may update, change the delay here, and then increase the latency of the whole flow. So we try to maintain the network schedule. And the solution, we call it Windows precedence occlusion, WPX, which is made of three principles: Windows precedence occlusion, plus two other things: window enlargement and protective gating, that I'm going to present. So what is the main idea? The main idea is not really new, it's just use some slack. Okay? We want to reserve a time window larger than what is really required. Okay, and we say, okay, but we lose bandwidth. We have a solution, I represent it. And this slack will be used to host the new data flows. What are the challenges? I've said, okay, slack is going to waste bandwidth, so we don't want this reserved bandwidth for future use to be lost. We want to be able to use it if there is no fault, in fact. And we want to share window between several flows. We'll do that to avoid the problem of link, the fragility related to losses. Oh, sorry, too quick. So what is the idea of Windows precedence occlusion? Quite simple. We don't want to have any overlap between two windows if there is one frame coming from one window to another window. So here is an example of overlap. Sorry, that's the good button. Okay, the right button. So if we have window 1 on a link between H0 and switch, okay, we may open another window, this is window 3, just after reception of A. Then we have, the good point with that is that we have very small latency delay in the switch, but we have overlap. So we'll try to do a schedule like this, and we call it precedence occlusion. What you have to keep in mind is that with such a constraint on schedule, when a window is open at the start of the window, all the frames that should be sent in these windows are already in the queue. And which is not the case here, because when the window opens, just A is in the queue of the switch. B and C will come just after. The second principle is to enlarge windows as much as possible, meaning that if we have time, we are not obliged to put the window just one after the other, if we have time. So we can introduce spare and enlarge the windows to use this spare. So what we say that, okay, but sorry, what about this time? That's some bandwidth that is lost because it's reserved for future use. And then we come with a third element, which is called protective gating. So I have to explain how, in general, tasks protect from lower priority flows. So first I have to explain what is the problem of protection. So imagine that we have the high priority flow, which is scheduled with tasks, and here we have another flow, a lower priority flow that could be a CBS or best effort, or okay. If you have non-preemption, or even with preemption, because there is always a minimal size of related to non-preemption, to preemption. So, but assume you have non-preemption. When the time window for A1 open, perhaps that there is a frame of low priority flame that is being emitted, and then A1 can start its emission just after, only just after. So what is commonly done is called exclusive gating, meaning that when the gate of a task frame or task queue open, then all other queues are closed. And then you have full protection. What we say that it's not completely necessary. Perhaps we can close the gate only at the beginning of the time window. Then we will have no frame that will encroach to the task time window. And because this queue has higher priority, then it will keep the priority, it will keep the link up to sending all frames. And as already said, all frames are in the queue at gate opening. So this part that is not used can be used safely by lower priority flows without affecting task frames. And that's all. We have all these three principles that allows us, in case of failure, to change the routing and allocate resources without changing the window. So how it is done? So we first have to build an initial schedule. So I will not give a lot of details. There are in one technical research paper you can find, but we do use some constraint solver and do some post-processing that build such schedule and enlarge windows. And yes, what I've not said is that we also add some empty window on some links, because if there is a link that is really not really loaded, it will reserve a few windows, okay, and not enough windows to host new flows. So we can add new flows, to add new flows in the future. We create new windows, and when there are some faults, we identify the set of flows that have lost a link on the path. And for each flow, first, of course, we free resources that have been designed, reserved for this flow at this time. And then we try to find a new route, a new path, and to put along this new path the frames in the slack of the windows. Does it work? Yes. So on the topology I presented, we have systematically pick out one or two links, considering that these links are broken. And the question is, how many flows? So we have, in this example, we have two task queues for queues 6 and 7, and how many get a rescue schedule? Of course, there are a few cases when there is no more path. So if there is no path, we cannot allocate any resource. So we just, when we are making statistics, we make only statistics considering the set of streams that have a rescue path. So depending on, so I have more detailed in papers, but what I've presented today is several ideas. So we have a simplex solver. So if we use only the simplex solver is not very good at creating free space. So we are not able to compute rescue schedule. But if we enlarge the window, we are able to save, okay, let's say 10% of the flows. If we add window, we can go up to something like 20%. If we combine adding windows and enlarging window, we can save, I will say, 1/3 of the flows. So to conclude, TSN reconfiguration is a global challenge, and the contribution is only reconfiguring a subset of TSN, which is the time array shaper. we have presented a novel task schedule scheme called Windows precedence exclusion. It has a lot of good property. It's incremental. It's immune to frame losses. It has no coherency problem when we can go from one configuration to another without having any problem of coherency because, in fact, we didn't change the GCL configuration. The performance are still under evaluation because I've presented some result, but we are working on slight improvement to improve it and to have a better understanding of what can be done with this mechanism. And also, this mechanism, I was thinking about that, but I did not update my slides because it's also used during, not for fault, but during design. So people from Thales are very interesting from this are very interesting by this principle at design time, because at design time it also allows you to do several add of new flows without changing anything. So of course, at some time, if you add too much flows on a configuration, you have to change the global schedule. But you can do minor changes without changing the network configuration. And so we are working on a possible improvement. And that's the end of my talk.
Thanks, Marc, for your presentation. So do we have any questions in the room? Yeah?
Yes, please. Albrecht Schwarz from ETAS. So if we would map that use case in automotive or mapping it to an in-vehicle network, this would be a network-wide topic, network reconfiguration, so typical network management topic or network control topic.
Yeah.
And if it has to be done by an onboard instance, it would be done by a fully centralized in-vehicle network management manager. I'm not wondering about the algorithmics behind the algorithms for resource management, but there was the question about the capability of Young-based management data models. So if you have here a network management topic, you require, of course, management data models on the level of a network. Yeah. So we have here quality of service management, we have fault management, we have resource allocation management. So if that network management manager would do on a Young-based modeling basis, we would see here typical Young topology models require a topology model, a topology of the communication matrix or the traffic flows. We require a topology model which allows to denote properties of a network like resources, so traffic engineered capable topology model. So this might be a good example, yeah, to see also that Young is basically used for network management, yeah, and not only for network device management, yeah, like an automotive switch management. So this is just a complementary comment because this is TSN and Young. Yeah.
Okay, thanks.
Yeah. Another question? Last question?
Yeah. Thank you, Marc, for the nice presentation. A question with respect to the properties that you would apply, especially the Windows precedence exclusion. There probably is going to be an impact on the performance in terms of latency and jitter, or maybe, well, latency and maybe jitter of the low priority queues. Have you evaluated that?
So the problem is not especially a problem of latency. In the use case that we had, we are able to satisfy all the latency. The problem is mainly a problem of load. We cannot achieve very high load, in fact, because with this exclusion mechanism, we are saying that there are some forbidden time slot. Okay, I cannot. Sorry. Okay, so I have no time. Okay, but yes, I cannot use this time slot. okay, for TAS. So it's good if, I would say, TAS is representing something like 20% or 30% of the load. Okay, if you plan to use high load of with TAS, like 60 or more than half, in fact, it will not be a good solution, except in very specific topologies. Okay.
Thank you.
Yeah, then one last from José.
Can you go back to slide 11, I believe? Yeah, this slide.
Yeah.
Thank you. So I have a question. When this is interesting to the precedence exclusion, but how does it affect to the buffer in the switch?
Oh yes, we need more buffers than common TAS.
So silicon vendors, can you provide more buffers to?
But in TAS there is no burst. Okay,
yes.
You can really manage the maximum size, and in fact, what we had in experiments that buffer size are something like 5-6 frames, no more, or otherwise. And moreover, you can ask your Cplex solver to have a maximal size on Windows, because it will be your maximal buffer size, and it will schedule a solution in this way. It was not a constraint that we have added in the solver currently, but it's easy to do.
Okay, thank you. Thank you very much.
Thank you. So now I will give the mic to José for the next part.